Welcome, and of course, we are for the very last Kaiser Spring Lecture of this year, with the theme Back to the Moon, in honor of the 50th anniversary of the moon landing. The past weeks we have looked back at the history of lunar exploration. We have learned about the moon as a great giant particle detector, and we have learned about the detection of distant exomoons. Today we are going to end the series with a look at the future, and our speaker of today is an astrophysicist from and a big moon enthusiast, I think I can say, from Leicester, and he has been working for the European Space Agency for 10 years now here in the Netherlands, so and has been leading various projects that have to do with lunar exploration. And today he will share some of his knowledge with us. So please welcome James Carpenter.
Thank you for having me. My name is James. I'm from the Human and Robotic Exploration Directorate in the European Space Agency. I'm based at ESTEC, which is about 10 kilometers from here, over in Noordwijk. It's about 2,500 people working on the site there, doing spacey stuff. Most of them probably aware of that already. So you also just heard I've been working here, working in ESTEC for about 10 years. I'm going to do this in English. The reason for that is I have two children, they're 4 and 6, they speak excellent Dutch, and they find it humiliating when I try to speak English. So it's better for everybody that I do. Okay. So thank you very much for entering into this already. It's always very interesting for me to understand who I'm talking to, what people's ideas are, what the moon means to them. The moon actually is interesting, it has a unique cultural significance across the world to everyone. It's the only place that everybody on Earth has seen. Right? It has this kind of very unique place in our cultures here on Earth. This is kind of an icebreaker. I'm going to go to the next one now. I'd like you all to participate. I'd like you to try and explain to me what you think exploration is and what it's all about. So in ESA, we're unique in the world in that we have 22 different countries that we serve. We are an agent of our members. That's 22 different countries with 22 different cultures, 22 different ideas of what exploration is. And all of them have different ideas about that. So for some countries it's all about the science, for other countries it's about national prestige, for other countries it's about driving technology, for other countries it's about other things to do with geopolitics or other things like that. So I think that is everybody has a different kind of idea of what space exploration is about. And every time you ask a group of people, what do you think exploration is all about, they'll always tell you something different. And you always have this spread of ideas. This is also a good way of understanding exactly how many people we have in the room. So I think there should be 75 people here, which is brilliant. Okay. Is anybody trying to fill this in who hasn't done it? So what you see here, so we'll come back, we'll use this again. So, but what you see is that even in the room, we have kind of a spread of interest. And what's interesting is this new scientific knowledge part is a really important factor. And that's generally pretty true of the public. For politicians, it's often not a major factor. They're often interested in things about geopolitics, which actually isn't mentioned here at all. Okay, cool. Thank you for that. Right. So what I'm going to try and do today is I want to give you a bit of an overview of the history of what we know about the moon, what we learned from Apollo and the work that's done in the past, give you a bit of a snapshot of where we are today, what's happened recently, and a view to what's coming in the future. And I think it's quite exciting. So you've already told me what is exploration. And I'll tell you what exploration is. This is exploration. This is Apollo. So Apollo 50 years ago. I was in the USA last week in Houston at the Lunar and Planetary Science Conference. This is a conference that started just before Apollo 11. It was the 50th one this year. And I had the opportunity while I was there to have lunch with Jack Schmitt. Jack Schmitt was the only geologist who ever went to the moon. He was on Apollo 17. He has some very strong opinions about various things to do with politics and things, which are not so great. But he's an extraordinary, inspirational guy. And that evening I went to watch the Apollo 11 documentary, which isn't out in Europe yet, He uses original footage, all taken at the time, to show you what happened during this Apollo era, to this Apollo era, that first mission. And there's one scene where the Saturn V rocket is sitting on the pad and then it starts to launch. And this is original, I have to keep reminding myself, this is real, this is real, this is real. And it's a skyscraper going up into space, extraordinary. And I thought to myself, I had lunch with Jack today, Jack sat on one of those. Wow. I mean, this was really, it didn't happen too early. The world was not ready for this. Right? This is, I think what's really important was this was driven by a very unique set of geopolitical circumstances. It was the race between the United States and the Soviet Union trying to show whose worldview, whose ideology, whose political system was the superior. That's what it was all about, and that's what drove it. It wasn't about science or discovery, it was about proving a point and making sure that you were there first and that you won the race. However, Apollo was also probably the greatest scientific set of missions or scientific program that we have seen in the last century. It gave us the basis of the whole of planetary science. It started off that whole field. And so what I want to do is try and give you a bit of a taste of what we learned after Apollo, what we think we know about the moon and its role following the Apollo missions. So the first thing we learned is that the Earth and the moon share a common origin, a common history. So what we think, looking at the rocks that came from the moon and the rocks that are on Earth, we see that they are chemically very similar. And the isotopes, the different elements and the way that their masses are aligned is very similar for Earth rocks and for moon rocks. So if we get a meteorite from Mars or a meteorite that comes from the asteroid belt somewhere, we look at the isotopes in these rocks, we can find that they are very different from each other. We can identify that they come from a different place in the solar system. But the moon and the Earth are very similar. So we know they must have had a common origin. And the idea that has been the dominant one since Apollo, that's actually backed up the best by the data, is that the Earth and Moon were formed during a massive collision, where a body about the size of Mars, which is something called Theia, slammed into the early Earth, threw debris up into orbit around the early Earth, and this coalesced accreted to form the Moon. Now there is a mystery here, however, in that all the computer models that have been done and how this collision must have occurred tell us that Theia should appear in the signature rocks of the Moon. It should be there, so we should have to find it in the chemistry of the Moon. And so far, it has been very difficult to find. There are a couple of papers saying, we found it, and then they were disproved later on. So there are a couple of things recently in the last year or so indicating maybe we found traces of Theia. But this remains a bit of a mystery, is that the Moon actually looks too similar to the Earth. We should be able to see something of this. So there's still a mystery there about where the Earth and the Moon came from. Which is remarkable, because we don't even know today the origins of the Earth and the Moon in any real detail. So then after that happened, there's a story I'd like to tell you about how the Moon and evolved over time. This is a video I thank our colleagues in NASA for producing this video, which basically gives you an overview of the sequence of events on the Moon after its formation, which is what we've interpreted basically from the Apollo samples. So the first thing we have is a accreted early Moon. It's very hot, and I think called a magma ocean, which then starts to cool. And as it cools, you get the crystals of rock start to form, and the light ones float to the surface, those contain aluminium and silicon, and then this happens. This is the South Pole Aitken Basin Formation. It's the largest crater we found anywhere in the solar system. It's on the far side of the Moon. And the formation of this body starts a period which we call the cataclysm, or the late heavy bombardment. This is a period where we have very large impactors smashing into the surface of the Moon, creating enormous what we call basins. And those are, you can see them now, they're very obvious large structures that we see. So after these events come to their conclusion, we start to find that there's a magma starts to erupt from deep within the interior of the Moon to fill these basins. So whereas these light areas, these early parts of the Moon are very light because they contain aluminium and silicon, the magma that comes up from deep within the Moon contains heavier stuff like iron, titanium, uranium, very heavy metals and things. And those are much darker, so those are the Mare, the dark regions that you see on the Moon today. Those are these deep material from very deep below coming up to the surface. We then go into a period of intermediate cratering. This is where there's a constant raining down of space. So not the huge stuff we saw before, but this is raining down constantly onto the surface, and it churns up the surface, creating the scarred, pitted, mountainous and cratered landscape that we see on the moon today. It also churns up the surface to create this dusty, powdery, fragmented material that covers the whole of the surface that we call regolith. And then more recently, in the last billion years or so, we have this more cratering on the surface, but these are much younger, so they produce these areas where you see these light-coloured rays spraying out from these craters. So these are much younger, they haven't had time to get darker because of their exposure to the radiation and environment of space. And that is how we came to the moon that we see today. And one of the reasons that's really important is that everything that happened there also happened here. This is kind of an artist's impression of the early Earth. So while all those things happen, while those impacts are taking place on the moon and the surface being churned up, the same thing was happening on Earth. So while these big basin-forming impacts, this late heavy bombardment was occurring, it was happening on Earth too, and those impacts coincide with the earliest observed traces of life in the isotopic signatures in some of the very oldest rocks on Earth. However, because the Earth is tectonically active, we have oceans and atmospheres and things like that. The surface of the Earth is actually geologically very young, because the surface of the moon is very ancient. So this epoch of Earth's early history has been lost pretty much from the geological record of Earth. So if you want to understand what was happening on the early Earth, the only place you can really go to do that is on the moon. In fact, very recently, I don't know if you maybe saw it, but a few weeks ago there was an announcement that in one of the samples from Apollo, it was an Apollo 14 sample, recently a rock was identified, which, when it's been tested, looks like it might be the oldest ever rock from Earth found on the moon. So following all these big impacts, it's been thrown up into space and landed on the moon. And so even though these rocks do not exist on Earth anymore, it might be that if you want to do the geology of the early Earth, we have to go to the moon to do it. The other thing we know about the moon is it tells us it forms a record of solar system and cosmic history. So because the moon has not been very geologically active, it's also very, very ancient. So the surface of the moon has sat and exposed itself to cosmic radiation, to the solar wind, throughout its history. So as the solar system has moved through the galaxy, it's gone near supernovae, it's passed through nebulae, through dust clouds, and that material has swept through the solar system and it all accumulated on the lunar surface. At the same time as the sun has changed over time, solar wind has been thrown out from the sun, it would have impacted on the surface of the moon, and again, it would have been kept and stored there over time in this regolith. Now, these are areas that are of particular interest if you want to look at this cosmic history. These are called paleoregoliths. So what happens is, this is a picture taken from the Lunar Reconnaissance Orbiter looking down at the moon from orbit, and you see this kind of layered structure. This is an image taken at the same place during Apollo 17 by my friend Jack. Looking across the this is an area called Taurus Littrow, and you're looking here at this layered structure again. What's happened is, you have a surface, it's getting churned up by these impacts, and then it sits there, and then it absorbs things. So you have the cosmic rays and solar wind, everything's being captured in the surface. Then it's an eruption of some sort that gets covered by magma, and the process starts again. Then there's another eruption, and another eruption, and another eruption. And over the billions of years, or hundreds of millions of years, you get these accumulated layers, and each one of those layers records a discrete period in the history of the solar system. And so if you could take a core through one of these things, you would have a history of cosmic, of the inner solar system captured in this core. So we know that the moon is somewhere that tells us about the early Earth, it tells us about the formation, the early evolution of the Earth and the moon together, and it also tells us the history of the inner solar system since the moon's formation, just under 4 billion years. We can also use the moon. So there is a community, actually the Netherlands is very strong in this area, who do long wavelength radio astronomy. And so one of the problems with long wavelength radio astronomy is that long wavelength radios don't penetrate through the atmosphere, so you really want to go to space in these measurements. And also the Earth is very noisy in long wavelength radio. So it turns out the only place you can go in the solar system where you can't see the Earth is on the far side of the moon. And so this is a radio telescope called LOFAR. It's part of a radio telescope called LOFAR. If you go downstairs to the visitor centre here downstairs, I think you can see one of these antennas. These are arrays of very simple, actually, wire antennas for measuring radio from the cosmos. This is part of a European scale, continental size telescope with nodes in the Netherlands and in various other countries across Europe, which all network together to create this massive telescope. Now, because we're on the Earth, there's a fundamental limit to the science you can do here. So what he's realised, this is an artist's impression, a great artist, but an artist's impression of what one of these things might look like on the surface of the moon. So this community, their next place they'd like to go is the surface of the moon, on the far side, to do these measurements. And in fact, right now, on the Chinese Chang'e 4 mission, there's a lander and a communications relay orbiter. On the lander, there is a radio telescope, or a radio antenna, which is trying to characterize the environment there, ready for these long-range measurements in the future. And on the orbiter, there is a radio antenna, which has not been activated yet. It activated in a few months, I think. And that radio antenna was built in the Netherlands and led by a group of 9. So that's something you can also be very, very proud of. And that's the first measurements of radio on the far side of the moon. And that opens the whole era of cosmic history, what's often called the cosmic dark ages, when the first cosmic structures were formed in the universe. So that, in a very quick nutshell, is kind of what we knew after Apollo. And there's more besides that we're supposed to know. But after the Apollo era, of course, not a lot happened. So Apollo was at its peak was 5% of US GDP, right? So give me 5% of European GDP, I'll give you a great moon program. So that's not going to happen, right? So that was not sustainable because the motivations that drove it to happen, once the game had been won, once they'd done it, the Soviets gave up. Okay, so the political incentive was not there. There was also at the time of the Vietnam War, that was also quite expensive, and so the whole thing it came to an end and petered out. And then there was a long period where not a lot happened on the moon. However, in the 90s, you started to see a few missions going back there. So there was the European Smart 1 mission, ITER was a Japanese mission, Lunar Prospector was a mission that was looking to understand what the resources of the lunar surface might be from orbit. These are all orbiter missions. And Clementine actually was not a NASA mission, it was a US Department of Defense, an Air Force mission. Actually, interesting, there was some of you might remember during the 1980s, there was the Strategic Defense Initiative called Star Wars. And Star Wars was, the program was where you can detect nuclear activity or nuclear missile launches in space and exactly see it with lasers. It's brilliant. Completely unfeasible, but brilliant. And but one of the things that they did, the Air Force built these satellites that were designed to look for activity related to nuclear. So they were full of these instruments to look for things like gamma rays and other things. What they did is they took one of these spacecraft, they repurposed it, and they sent it off to the moon. That became Clementine. And Clementine was the first mission really to map the moon in gamma rays and to look for the signs that there could be water at the lunar pole, something which Kaiser Lente Prospector both did. We'll talk more about that in a moment. And then if you go into the more recent, in the last 10 years or so, there's been an increasing number of missions. So we had the Japanese Kogoya mission, we've had a few. Lunar Reconnaissance Orbiter is operating at the moon now, has produced the largest data set of any mission ever to anywhere. It's an extraordinary data set it's produced. Grail to map the gravity of the moon. Artemis is operating now, looking at the plasma environments in the vicinity of the moon. L.A.D looks at the dust environment around the moon. And then this was really L-Cross slammed into a crater in the South Polar region to look for water, ice, and found it. And then what's really interesting is you start to see the emergence of new space powers. So Chang'e 1, Chinese orbiter, Chang'e 2, another Chinese orbiter. Chang'e 3 was the first lander on the moon since the lunar missions of the 1970s, so it was Chinese. And then Chang'e 4, January of this year, first ever mission to land on the far side. And China are very impressive. They started from a very low position, and about a decade ago, they made a roadmap, a strategy. And now they're there. they just keep going. So, I mean, it's been really impressive watching them come from nowhere and start to really sort of ramp up their activity. And their plan is during the second part of the 2020s to build a robotic lunar research station. I'll be talking to them about that. I'd say that I'll talk in a moment about some recent events in the USA, but that's in no small part due to what's coming here. I also see Chandrayaan-1 from India. Chandrayaan-2, that was an orbiter. Chandrayaan-2 lander is planned for later this year. So this is the beginning of something very international and very, very big. So what we can, before I go to that, maybe I'll just say this has not been without its impact on the science. Right? So this is just an example. This isn't science, but this gives you an example of the kind of thing that's possible now. This is an image taken of the Apollo 14 landing site by the Lunar Reconnaissance Orbiter from orbit around the moon. And here you can see this is the lander, that's the descent stage. The ascent stage, of course, is no longer there because they came back. This, and then we do the close up there. This is called Allstep. That's a little geophysics experiment package that was deployed on the surface by the astronauts. And these little streaks are astronaut footprints. How cool is that? So we can now observe astronaut footprints from orbit around the moon. Now, when you have that kind of capability, that has an effect on the science that you can do. Right? So here I'm going to give you a couple of my favourite things that have come in the last 10 years or so, right, from this kind of new data set. Right, this is the first one. So this is a map taken in gamma rays of the moon from orbit. Well, this is actually from Clementine, which is this Department of Defense, US Air Force one. Right, and what it shows you is the abundance of thorium across the surface. So thorium is, it doesn't really like to go into rocks, it's very compatible, so it comes up with sort of from the deep interior in eruptions. You'll see most of the moon, not a lot of thorium going on. This is the near side, so that's the Mare, the dark bits that you see normally, and you have this big, there we go, and you have this big area here where there's a lot of thorium. So that's because this material has come up from really in the deep interior up onto the surface. And thorium is just one of the things we find there. We find these areas are very rich in something called creep. So creep is K-R-E-E-P, or potassium, rare earth elements, and phosphor. It's a very exotic kind of weird stuff that comes up in the deep interior of the moon. On the far side, you see that a little bit more again. This is not mostly volcanism. That's the South Pole Aitken Basin I showed you earlier, this massive impact. That's where the impact strips away the upper crust, and you're looking into the lower crust and maybe even the mantle of the moon. So the moon actually is a model, because it ended its geology fairly early in its lifetime. It provides us with a benchmark for planetary formation and evolution. It's kind of the basis upon which we understand all planetary formation and evolution. So if you can start to access these bits, these different layers of the structure of the moon, that's really important. What you're seeing is a spontaneous gamma emission from the thorium, yes, which is one of those. But what it shows you, actually, so what I can tell you is that all of the Apollo missions, which brought back our samples, and all of the lunar missions that brought back less samples from the Soviet Union, they were all located around here. So the only thing that I can tell you definitively about all of the samples, the ones that we've used to create this whole chronology of lunar history, this chronology of the history of the Earth and the Moon and their relationship with each other, all of those things, about the whole story I just told you, all come from here, and what I can say definitively is they do not represent the Moon. So if you want to do the science, if you want to understand the science of the Earth and the Moon, this narrative, better, you have to go back there, and you have to go to places that we haven't explored before. And the first mission outside of these zones is Chamber 4, and it's in here somewhere, right now. The other thing that's really cool has been the discovery, the quest for lunar ice. So let's see, this is a very old idea. The idea that the poles of the moon can get very cold and very dark. So if you have craters in the poles of the moon, because the inclination, the tilt of the moon is not so much, if you're standing at the poles, the sun basically moves around you like this. So if you're down a big hole or inside a crater, it can get very, very cold. So the idea is that at the poles of the moon, then you can trap water ice and other volatile chemistry. And this was first postulated in a paper that the earliest reference I've seen to this was from a paper in Nature from 1897. So it's quite an old idea. Picked up a lot of speed really in the 1960s and 70s when we started talking about it again. The first measurements that that showed that there was probably something there came with Lunar Prospector and Clementine. So Clementine used radar to sort of traces that maybe there was some water ice in some places. Prospector had a neutron spectrometer, and it looked at the neutron fluxes that were coming from these areas, and those were used to infer there was hydrogen there. So not water, but there was an excess of hydrogen in these regions. More recently, what you're seeing here, this is a map showing where water ice could be stable at geological periods of time based on the surface temperature measured from orbit lines, from the lunar reconnaissance orbiter called Divider. And so these pale blue areas are permanently shadowed places. Some of those are, as condensate, so 25 to 30 Kelvin, so extremely cold places. And this is where you could keep water ice stable at the surface for billions of years. These darker blue places are areas which see some sunlight, but where within 1 meter of the surface, you could keep water ice stable for billions of years. So we have inferred now that there is a lot of water ice probably in the polar regions, but we don't exactly know its distribution, where it is, how much it is. The only thing we do know is that this one location here, Crevaeus, the L-Cross mission slammed into that crater, threw up dust and debris, and then the composition of that plume was measured. We know from that plume that there was about 5% weight of water ice, along with lots of other chemistry in that plume. So that gives us that only ground truth really in that one location. But this is really interesting because water is, of course, it could be useful for future exploration. So water we drink, it's all hydrogen and oxygen, which you can breathe. Perhaps most importantly, hydrogen and oxygen is rocket fuel. So this could be, on the moon, a cosmic fuel station for future exploration. And so that is why the poles are becoming really hot property, like prime moon state. We also find that in this area, if you're on a mountain in this area and the sun's moving around you, it also never gets dark, so you have nearly continuous solar power. So you have continuous solar power next to fuel. That's important. That's quite strategic, which is why one of the decided to see a lot of interest in the poles. It also provides a record. We don't know really where this came from. It also provides a record of volatiles, chemistry in the solar system. It can give us a record of the life-enabling chemistry in the solar system. It will also show you in a laboratory where if you take organics and things, stick them in ice, you can expose them to impacts of the cosmic radiation for geological time. Can you start to create prebiotic chemistry in these environments? And that can tell you something about the origins of life-enabling chemistry in the solar system. Outside of the pole, these zones also have regolith, which I talked about, which is all over the moon. This is being more and more looked at as a potential resource. So regolith is made of rocks that are ground up, and you find that it's made, basically if you look at it, it's made up of mostly oxygen, very useful, and metals, also useful. So if you go to the right places on the moon, you can take just the material you find there, you can split that apart, you have oxygen, for life support and rocket fuel, oxygen being the most massive part of rocket fuel, and you have metals which you could use for in-space manufacturing of things. So the moon is probably in the early missions the first place where we could start to learn to access and utilize resources that we find in space to use in space. And so if we want to really become a spacefaring species, the moon is where we're going to go and learn how to do that. And that might come soon, I think. So these missions I've just shown you, this is very difficult to decipher. What I want to try and explain this is that they are at the beginning of something. So I showed you these missions that have happened very recently. The Chinese landed Chang'e 4 on the far side in January of this year. There is an Israeli lander called Beresheet, which is on its way to the moon right now. That will land, that's a plan where they will try to land next month. That's actually very interesting. It's the first ever private sector moon lander. So that was not paid for by the Israeli government, that's paid for by a private non-profit organisation and built by private industry. So that's a really first. And that marks the start of a new trend of commercial or private sector lunar access. So we have all these different things on this side here. These are all missions which are currently planned, which are private sector driven and not driven by governments. Actually, NASA just started a program called the Commercial Lunar Payload Services Program, where they are planning to buy flights for science payloads to the moon on private sector landers starting from this year. On the other side, we have a bunch of missions driven by governments, which are from, you see there's lots of different countries there involved. Now what I haven't accounted for here is what happened this week, which was this. Now, I don't know if anyone spotted this, but NASA said a while ago they plan to go back to the moon. So, Space Policy Directive 1 from the Trump administration was go back to the moon. And so NASA started planning, and the plan, at the end of last week, was 2028 international missions to go back to the moon, led by the United States. And that's great, because the rest of the world was planning to do that anyway. They were kind of waiting for the United States to catch up. They've got this political thing going on there. So, the space policy, whatever you think about the administration, the space policy makes complete sense and is aligned with the rest of the world. What happened this week was that the National Space Council in the United States, Vice President Pence stood up and said, we will have humans on the moon by 2024, whatever the means. Right? And they're also very clear, NASA, if you can't deliver this, we'll find someone else to do it. Right? And it was a very, very strong message. Now, is that physically possible? I have no idea. Right? That's quite quick. Now, in the 1960s, they did it in 8 years from a standing start. So you'd think it's possible. It's a little bit scary for us because we're not quite ready for that yet. But now it's thrown everything in the air. The whole world right now is going, okay. We were all planning to do it together, but if they decide to go that fast and it's not impossible, then the rest of the world will have to respond. The nice thing is the US are very clear they intend to lead, but they want this to be an international endeavour. And there's been a lot of work going on during the last 10 to 15 years to make this an international endeavour, and the rest of the world is aligned behind this. So what we in Europe try to do, we in ESA. So the first thing we're trying to do is to create commercial partnerships at the moon. So we're working with private sector companies, industry, to prepare missions to go to the lunar surface. We're trying to understand at the moment, how can we partner with some of these companies in Europe to make sure that they have a role to play in this ecosystem that's emerging around the moon, and how could we, as an agency, buy flights to the moon for scientific experiments and things from some of these companies. Because it's non-trivial, it's a completely different way of working. Today, even if I wanted to buy a flight on a mission to the moon from a private sector company, I couldn't do it. So how do we need to change, how can we do that? The other thing we're doing is we are building something called Prospect. Prospect is a package that is being built to go to the lunar South Polar region, to drill into the surface there, to take samples, to do scientific investigations on their samples using a chemical laboratory, but also to investigate their potential as resources. So we're looking at things like water ice, how much is there, what are its properties, and looking at some of the chemistry that underlies some of these processes of extracting oxygen in metals to see how we can do that. And that is a package which is being built and ready for flight on a mission called Luna 27, which is being led by Russia. So we're partnering with Russia on that. That's something very important. I mean, Europe and the European Space Agency is, I think, unique in the world in that it has international cooperation at its heart. And I think we see part of our role in the future as being something which brings countries together. So we are working very hard to do space exploration, but to do so in partnership with other nations, so that we can make space exploration an international endeavour. It's a peaceful endeavour, and we have a very important role to play in that. So we're working very hard to partner with Russia, the United States, and increasingly we try to work with China as well. We're also working on something called the Gateway and Orion. So Orion is the NASA crewed vehicle that's going to take humans to the vicinity of the moon. That's being built now. Well, it's been built pretty much. It's being put together. This bit at the back is called the European Service Module. That is ESA are building that. That contains the life support systems, propulsion systems, power systems. And the first one of those has been built and delivered to the United States. That's a European Space Agency provided item. It was built in Bremen in Germany for the most part. And that will go to this thing. It's called the Gateway. The Gateway is something which we plan to build, working through the partnership that we built with the International Space Station during the early 2020s. Be a crew-tended platform in the vicinity of the moon, from which we'll have missions going backwards and forwards to the lunar surface, starting, if you believe Pence, in 2024. But we were originally planning for a little bit later than that, so let's see how that works. We're also then, as you start to prepare to go to the lunar surface, we're working on missions again with international partners to see how can we start preparing for that. So this is a study that's been going on with international partners. There's something to how do we rehearse the technology and the operations of those human missions in order to prepare for them later on. So this is a study where we have a lander and a rover an ascender to bring samples back to the gateway. The idea is that this is a study to look at how we can develop the technologies and practice them in advance of the human missions. And we're currently in a process, working with national partners to look at how does all this work together, how do we work together to do those early human missions, and what is the pathway to get there together. And finally, it's the next destination for humans. It's where we're going next. And so we're starting to work now, increasingly with our international partners, and especially with NASA, to work out what do these early human scenarios look like, and how do we work on them together. And so internationally, just to give you some idea, internationally, this is something that's been going on everywhere. This is something called the Global Exploration Roadmap. It's put together by the International Space Exploration Coordination Group, or ICG. So a group of 15 different, or now 16 different space agencies around the world. And it presents, and you can Google Global Exploration Roadmap, you'll find it as a document. This is the key figure. And it tells you what internationally we think space exploration looks like over the next decade or so. So we have International Space Station continuing transitioning to different kinds of future platforms in low Earth orbit, the Chinese space station coming online during the mid-2020s. At the same time, we start to go to the moon. We built the Deep Space Gateway, and use that to access the surface of the moon, with the transition then going into human lunar surface exploration from the late 2020s, with the Gateway using that as a support service to enable those missions. And that goes on to the right. Space exploration of the moon should become something that's permanent. So when we go back to the moon, we're not going Apollo style, we want to go sustainably, we want it to last forever. And in preparation now, we have like robotic lunar missions, which are starting to see some of those to prepare for access to the moon. And then onwards, everybody in the world, all the agencies agree, we want to put humans on Mars, that's the goal for everybody. That's going to happen one day, but let's not think it's going to happen too quick, so that goes off to the right somewhere right there. And that's a big challenge, but you don't do that until you've learned how to do this. And maybe one day we have a moon village on the lunar surface. That was the vision of our Director General. But the idea is it's an inspirational vision for international cooperation, including multiple agencies, private sector, public sector, multiple partners working together in a cooperative way at the lunar surface for the benefit of humanity. That's the plan. Right, not ambitious at all. Right, so now I'd just like to basically give you a quick recap of some of that. So sit back and take me through. So the 1960s and 70s were an incredible era for space exploration, with the range of missions from the United States, which took close-up images of the moon, before eventually impacting into the surface. NASA's Surveyor missions demonstrated a controlled, soft landing of the surface of the moon, and tested the properties of the soil to prepare for future human missions. There were a series of solid landers and rovers, which visited a number of locations, performing scientific investigations, driving across the surface, and returning samples to Earth. But the pinnacle of this period of exploration was Apollo, and the arrival of humans at the surface of another solar system body for the first and the only time in history. Looking back now though, we see that only a tiny fraction of the moon's surface has been explored, all on the side of the moon that faces the Earth and in a region close to the equator. We've also discovered that all of the samples we've returned to Earth are from an unusual region with a complex chemistry of potassium, phosphor, and rare earth elements such as thorium. The vast majority of the moon has yet to be explored, including the entire far side. One thing that we can say for certain is that if we want to understand the moon, then we need to go back there. But now, after decades of waiting, an armada of missions from around the world, including ESA's Smart 1, have returned to explore the moon from orbit. Looking down from above, these missions are providing a wealth of new data, bringing a new understanding and raising new questions. They are giving us global insight and preparing for new missions to the lunar surface, led by China's Chang'e 3 and 4. And the next wave of missions, where might they go? The next destination will be unlike anywhere we have been before. extreme and alien landscape of the lunar South Pole. Here, we find areas of permanent darkness and extreme cold, where water ice and other chemicals can become trapped. And as we come up from these lowlands, we see towering peaks, basking in near constant light. On these polar mountains, the sun rarely sets below the horizon, providing the potential for near continuous solar power and a spectacular view of the rugged and cratered landscape below. In 2009, the L.Cross mission blasted water and other chemicals out of a permanently dark crater in the lunar South Pole region, allowing it to be observed by nearby spacecraft for the very first time. We also now know that there are nearby locations with similar cold conditions. Is there water here too? If so, how much is there? Where did it come from, and what can it teach us about the origins of water and life-forming chemistry on Earth? This water may have been delivered by comets and asteroids impacting into the surface over billions of years. It may even have been created at the surface of the moon. We now know that protons thrown out by the sun in the solar wind arrive at the lunar surface. Here, they react with oxygen in minerals to create a thin layer of water. These water molecules can be lifted by the sun's heat before falling again to the surface. And over time, these particles may move to the polar regions where they are trapped by the cold conditions. And as we stand at the pole, with the Earth in view, we can point our antennas to the sky to search for faint signals from deep out in space. The radio noise from the Earth is too loud and blocks out many cosmic radio sources. But as we move over the horizon, the Earth sets out of view, the noise disappears and a new kind of radio sky emerges. We see our galaxy and the planets as never before, and beyond, a quiet radio hum. A signal from the cosmic dark ages more than 13 billion years ago, when the first cosmic structures were formed. And now beneath us, the moon as we see it today, scarred by craters formed by billions of years of impacts. The largest and oldest of these, the South Pole Aitken Basin. Formed by a powerful impact around 4 billion years ago, many believe that its formation marks the start of a dramatic period of bombardment onto the Earth and the Moon, an era called the Cataclysm. This era is recorded on the Moon's scarred surface, and its end coincides with the appearance of the earliest of observed traces of life on Earth. In the coming years, we will see explorers of the lunar poles, exploiting the extended sunlight for power, performing research to benefit life on Earth and to understand our place in the universe. This will begin with small robotic missions to understand the environment and prove new technologies to pave the way for the future. We will then move on to increasingly ambitious missions with humans and robots working together, learning to live and work at the surface and performing new and important scientific research. This new exploration will be achieved not in competition as in the past, but in peaceful international cooperation. Eventually, we will see a sustained infrastructure for research and exploration where humans will live and work for prolonged periods. Here we'll put into practice the lessons of years on the International Space Station to establish a facility akin to those we see in Antarctica today. In the future, the Moon can become a place where the nations of the world can come together to understand our common origins, to build a common future, share a common journey beyond. A place where we can learn to move content into the solar system. But perhaps in the future, at a sun-bathed peak at the lunar South Pole at the edge of a crater, we will learn to access and utilize resources from deep below in the dark. Zooming in, closer and closer, we see water ice molecules trapped in the cold. A source of hydrogen and oxygen, essential for sustaining human life and for rocket fuel. Fuel to propel us further into the solar system, onto the next destination of our journey into the cosmos. So I started by asking you what you thought exploration was, and I'm going to finish by telling you what I think exploration is. I think exploration is a story, and I think it's a story about people. It's a story about individuals. It's a story of Neil Armstrong. It's a story of Buzz Aldrin. It's a story of Gagarin. It's a story of the big individuals from the missions who stand out and the big characters and the big explorers. It's also a story about how we are better together. Now I like this picture because this is the moon. In the top right hand corner you can see the International Space Station transiting across the moon. And there is one place I can think of where the United States, Europe, Russia, Canada, Japan, a big international group of people are working together every single day in cooperation and in harmony to do the extraordinary things. And that's there, and that gives me hope for all of us. It's a story about human ingenuity and creativity. It's about how when we put our minds to it, we can do extraordinary things. We can land on comets, we can land on the moon, we can fly past Kuiper Belt objects. Right? This is it, we can do extraordinary things, and that tells me that we are not doomed. There are things we can do, there are extraordinary things that can be accomplished when we put our minds to it as a species. It's a story about where we all come from and our place in the universe. It's the context in which we live. It's about the cosmos, its history, our origins, what it means to be human and alive in this huge expanse of space and time. It is a story about our future and where we're going next. Where will humanity be? Where will it go? What will my children and my children's children's lives be like? What will they experience? What will they see? And how can we make that possible for them? And I think it's a story that everyone is in. During the Apollo era, this is actually a very recent picture, but during the Apollo era, during Apollo 11, 50 years ago, the entire world were united for one moment. The entire world participated in some way in that mission through a new technology called television. How much more so now with the technologies that we have now, and the technologies we can't even conceive of yet, that will be there when this real voyage of exploration internationally happens. I think that the next era of space exploration will not be something you watch, I think it will be something that you do, that you participate in, and that's really exciting. And if that's true, then this is your story. I hope you enjoy it. Thank you.
First, we have some time for questions. Are there any questions?
I think you have very positive look on world then, with the last survey. But then I'm thinking, who in the end will still demand ownership of the moon? Maybe that's my pessimistic way of looking at it.
So, it's a great question. Somebody always asks that. The other one is about the ethics, right? That will come to. Right. So the ownership of the moon is it's complicated, right? So there's one kind of legal framework that exists about it, which is the Outer Space Treaty. The Outer Space Treaty was signed in the 1960s, and it basically says no country can lay claim to anywhere in space. So nobody can go to the moon and say, this is mine now. Nobody can go to any place on the moon and say, this is mine now. Where there's a grey area that's emerging is about, not about the place, although with the emergence of the private sector, and the idea that maybe you can use the resources of them, maybe there's markets coming in space, how do you manage those kind of property rights? How can you manage property? So something that happened very recently in the last few years, 2 countries have created a legal framework that says if you go to a place in space, we recognise you can't own the place. If you take something from it, that's now yours. And that's the United States and Luxembourg. I'm not sure what Luxembourg would be able to do about it. But actually one thing that's really interesting is that within Europe, Luxembourg have been really active. They have something called the Space Resources Initiative. So in the 1970s, Luxembourg took a gamble on telecoms in space. And they said, we think telecommunications is going to be a big thing. So we are going to gamble, we're going to invest in telecoms. We create an environment where telecoms companies will want to come and work in. And what came out was SES, which is the biggest telecoms company in the world, so they're based in Luxembourg. They're taking a gamble on space resources. They're called the Space Resources Initiative, where they are creating legal frameworks and taxation regimes and investment incentives to bring space resources companies into Luxembourg. And they know most of them is going to fail, but they think this is going to be a big thing over the next decade, so they're investing in it. And one thing that's done, also at political level, is it's really got other countries in Europe starting to think about this. And globally, between the United States and Luxembourg, they're not necessarily equally matched, but this is really driving a new thing. And so, for example, in the United Nations, there's a body which talks about the use of outer space, and this is a topic that's starting to be talked about very seriously. The question is, can the politics and the legal, the governance frameworks for this move as fast as the truth on the ground? And that's not entirely clear. Well, it's actually, there is a group which is talking about these kind of topics from a legal standpoint. It's called the Hague Space Resources Governance Working Group. It's actually based in Leiden, but no one knows what's over but actually, that's actually been led by the University of Leiden, by the legal faculty, and they have a multinational, multi-governmental, private sector and public sector group, which have been trying to create a framework that can then be taken to the United Nations and say, look, here's a draft framework for a legal agreement on space resources and governance and things like property rights. So there are people trying to make something happen in this regard. It's quite complicated. So the best way to see it might be a bit like the Wild West. So what happened was, the Wild West was a bottom-up thing. People just turned up places, started mining, and then on the local scales they had to start creating agreements about who owned what and how in order to kill each other too much. And actually what happened in the end is that the top-down legal framework just ended up being a codification of what we decided on the ground. And so there are some people who think that that's probably how it's going to end up. It's a challenge of the world. Yeah.
We have a famous space lawyer called Frans van der Dunk. Do you know him?
No, I don't. No, okay.
He's hired by all kinds of space organizations all around the world.
Space.
Dealing with this kind of restrictions.
I have a question about the next moon mission, because when 50 years ago, during the Apollo program, they were just taking off with the Saturn V rocket and going straight to the moon and orbiting and landing. But right now, we have a space station, International Space Station, and there are also, as far as I know, plans to retire the current International Space Station. So is it going to play any sort of role? Is there going to be any orbital rendezvous around the world? Because around Earth, because it's also, it costs a lot. They have to have a lot of fuel with them, like doing everything minimal, and they put extra burden on their program. Even when they were landing, they have limited fuel, so it could almost probably have.
So the current NASA architecture, and this may change, uses this thing which I'll show you the thing, the gateway that I showed you. So the idea is that you build this probably a staging post, a reusable staging post, which is in lunar vicinity. And then you go from Earth to this staging post, and then you go to the lunar surface from the staging post. And that you can the idea is to try and build reusability into the systems that you're using and to accessibility. So the gateway is in a particular orbit where it's much easier to get to from the Earth than if you go to the moon, or it's a very particular place. So there is an architecture that's been built up which is designed to have reusability involved and to enable multinational access and private sector access. So that's not the fastest. So Apollo was driven to be what it was by speed. It was all about get there fast. Now one outcome of that was that what they put together was not sustainable because they went, how do they let's get there as fast as we can. So the architect that's been talked to today is something that's supposed to be a much slower cost expenditure, so it's slower, but it has sustainability, it's called. Whether that's, now with this new thing, the 2024 date, I don't think anybody knows how to respond to that yet. And my fear is that that drives people to solutions that are speed optimized rather than sustainability optimized. So we'll do that. There's different ways you can do it. It also relies on having, for example, the US SLS launcher, which is your main launcher to get there. And that may or may not, that's also a discussion now a little bit. I think the US still plans to do it, but then there are those who are pushing to use smaller launch vehicles that exist now, which come from the private sector. And if you do that, then you'll be doing more assembly. You have to do more assembly in lower orbit to go that way. The International Space Station won't play a role in that. The plan is currently to do it in sort of 6 weeks. Watch this space department.
So what about the ethics?
Okay. So well, the ethics was, is it okay to go to the moon and dig a hole? Right. So one thing that really sort of strikes me is, I think you go back to this, right? So that's an astronaut footprint that's 50 years old. So what it tells you is, you dig a hole on the moon, not a lot changes. I mean, that's there, right? That's not going away. And you'll see it forever, pretty much. So is it okay to go and start digging up big bits of the moon? Is it okay if it's just on the far side so nobody can see it? If I kind of play I have a colleague who said she thinks it's wonderful that we'll be the last generation to have ever seen the moon without lights on it. Is that okay? I don't know. No, but I'm a huge advocate of space exploration and let's go travel the stars. It makes me feel a bit funny. So I think all these things we don't know, and I think that the legal and the government, the legal and the governance aspects of this they're happening quite slowly because there's never been a push. And I think this is starting to happen now. I mean, this is going to happen. And even if the US decides they don't want to go to the moon anymore, the Chinese are going. Like the world is this is a thing that's going to happen, and we need to catch up. And I think those questions are not answered yet at all. I think that actually in ESA we don't have the competency to talk about that. That's something for our member states, the government, the political level to decide. So we have to be a bit careful how we. So we can say there's an issue there, but we're not really allowed to take a position on it unless the states tell us what their positions are.
It's very difficult for long-term planning when you are dependent on governments that last 4 years.
Yes, this is where the Chinese have a massive advantage.
Yeah.
Right? So, because you see in Europe, we don't really have. One thing I see in ESA is the power of Europe to do extraordinary things when we really pull together as well. And as individual nation states pulling in their own directions, it slows us down tremendously, and we're not very efficient. If you take an equivalent-sized economy in the US, where you can have a very singular direction, because wow, you can really get stuff done before you right? Except there, so in Europe we have stability because everyone's going in different directions, and all these political cycles taking different times. So in the end, well, getting something started in Europe is impossible. Once you're there, you can't stop it. Right? So whereas in the US, flip-flops all over the place. The Chinese, they think when they strategize on 50, 100-year timescales. Right, so they have a plan, they go, let's make a 10-year plan with a 50-year horizon in mind, which is good. I went to a mission in 2010, I went to a big conference, the Global Lunar Conference in Beijing, and the head of the European Space Agency at the time, Europe, honestly. The average lifetime of a 30-year roadmap for exploration in Europe is 1 year. So, and then the guy from NASA stood up, and the deputy head of NASA stood up, and he went, well, you know, we honestly we just don't know what to do. We're going to do this, now we're going to do this, and I don't know. And then the head of the Chinese Space Agency, this is our roadmap. We made this roadmap 10 years ago, and now we are here. Oh, okay. And you look at the trajectory of this thing, and you go, wow. And they're going to do that. There's no reason to think that they won't. And I think that's actually the synthesis of the law. The challenge for us is how, because the Chinese have worked in isolation very much, and there are big challenges with the Chinese, from most of us are aware of. There's also big issues. So the US are not allowed to even talk to the Chinese. They're not allowed to have any contact at all. I think this competitive element is one of the things that's sparking this sense of urgency in the US. And I think that we in Europe are really important role to play here. It's kind of an interlocutor between all these different actors. And I think we're better able in Europe to do that than I think anybody else in the world. So that's good.
One more question is about what will the environmental impact be if you start to think about, I think, especially Chinese with their nice, schedules and in a hurry. So if you were to distract loads of fluorine, for example, and all the other elements that you might be able to find, if you distract them on a massive scale, really, you haven't been able to be very responsible with planet Earth. So what will the impact be if you were to distract loads of these materials on the moon, but not just the moon, the balance between Earth and the moon?
So firstly, I'd say I don't think we're very close to a situation where the resources we get from the moon have any value here. It's more about how we start to create infrastructure and capabilities in space using the resources of space. There are a couple of maybe possible exceptions to that, but there's not many. If you're on the moon and you dig something up, the difference is there's now a hole. So there isn't an ecosystem as such. There are things that you would change. So one of the things that the moon has is a very tenuous atmosphere. We call it exosphere, because the individual molecules, atoms in its exosphere don't interact with each other. They sort of hover around ballistic trajectories. And the total mass of the exosphere is about the same as the exhaust plume from a single Apollo lander. So one of the things, if you start exploring the moon with a regular cadence of missions, this environment will be forever changed. So one of the really high priority science objectives for these early missions is to characterize this thing, measure it. The alternative would be we just stop exploring. And I think maybe that's also where humanity may choose to say, you know what?
What I'm trying to ask basically is, can you explore in a sort of more sustainable way, so that the impact that the moon has as a planet orbiting Earth will be sustainable?
So I think this is a big part of how we're trying to do this. So the question we're asking ourselves, I think it's very early days. If you talk about early use of the resources on the moon, it's going to be very small scale. More like subsistence farming than industrial scale stuff. However, one of the things that we are exploring is how we can do this in a way. How do you learn lessons? And actually, how can you use, this is what's really interesting, how can you use the challenge of space exploration and resource utilization in space as a way of improving our approach to sustainability here on Earth? So one of the things we've been working with some companies on space resource utilization technologies. They're terrestrial companies, and they have no interest in space resources because there's no money in it for the next couple of decades. But what they do see is a tremendous synergy in terms of technology development. There's one company we're working with who have a process for producing metals from ores, and at the moment their waste product is carbon monoxide and carbon dioxide. And we were saying, well, could you do that in a way that produces oxygen as the waste product? Because there's not a huge terrestrial market for oxygen, but for us it'd be quite useful. Right? So, and they were like, well, that's an interesting one. And so they actually worked out a way to adapt their process so that they produce oxygen as a waste product rather than carbon dioxide. But they would never have done it normally because there's no cost incentive or there's no push to do it, but we give them a push, and now potentially they have a way of eliminating the greenhouse emissions from their production process in the long term. So I think areas like that, we're really trying to identify those areas as a way of generating some near-term benefits for us.
Thank you so much for the great talk. I really enjoyed it, and it's really exciting to hear about all the future plans. And I think it's also great to end this Kaiser Spring Lecture with such a positive message. Of course, you guys have done it for you.
Thank you very much.
And then some special gifts. Well, the WAD is kind of a tradition for the Kaiser Spring Lecture. It's something all the talks of this year.
Thank you very much.
And the special gift of this year is smoking. Hello, Devin.
That's it. Thank you. Actually, I was like, earlier, so I'm really thank you very much.
Okay, then some practicalities. We can go downstairs in a moment, and some of you already have a ticket to join the tour as well. But we'll start in past 3. So first you can get some drinks downstairs, and then join the tour. You already have a ticket. If you don't have a ticket, you still want to join the tour, that's also possible. And hopefully I'll see you next year. Thank you.